Great. So, since it's equicontinuous, we can use the definition. There exists delta larger than 0 such that when xy, the distance between xy minus is smaller than delta. It implies that fix, I is from 1 to n, fix minus fiy, distance between these two terms, is smaller than epsilon over 3, right? And this delta satisfies I think this delta actually works for f1 to fn, right? But we want to show that this delta actually works not only for f1 to fn. We want to show that this delta also works for all n, even now n is larger than the capital N. Okay, so this is what we're going to prove in the next step. We want to show that the delta we choose, which works for f1 to fn, actually works for all n. So now let's see what happened for n past the capital N. So for n larger than n, capital N, if we are still given dxy is smaller than delta, then we have, well, here comes a classic method, which is triangular inequality. It's still, I think it's a very fascinating method. It's kind of thrilling, right? So the absolute value of fnx minus fny is smaller than fnx minus f capital Nx plus fn capital Nx, f capital Nx minus f capital Ny, and f capital Ny minus fny, right? And we've seen that this is less than epsilon over 3, right? Here we got this. And similarly, for the same reason, we can also show that f capital Ny minus fny is smaller than epsilon over 3. And this one smaller than epsilon over 3 because the one we just showed here, right? So now we get fnx minus fny is smaller than epsilon. And now we are done. We prove that fn is equicontinuous on K by its definition, right? Through its definition. So fn is equicontinuous. Okay. Finally, we're going to move on to Ascoli-Arzela. So I'm talking to myself, telling myself that, okay, please calm down. It's a really exciting theorem, but you need to finish it very carefully. Okay. So Ascoli-Arzela. Now let's get started. Here we are given a sequence of functions fn, and it is a sequence of functions of it's a sequence of complex valued functions on K. And now the conditions are still very simple. K is compact, and fn is pointwise bounded on K. Then we can get two results actually. The first one is we can prove that fn is uniformly bounded on K. and result B is just what we are seeking for. Fn actually has a uniformly convergent subsequence, and is analogous to the result of Bolzano-Weierstrass theorem, right? And if you actually look into this theorem, you will find that the condition somehow is really simple. You only need like a sequence of functions, and the set of it is compact. K is compact, and Fn is pointwise bounded. Pointwise bounded, I actually think it's it's not a strict like condition at all. And this is what's like fascinating part of this theorem, because it's like push the boundary for the functions that contained that satisfy or that we can find certain like uniform convergent subsequence. This sequence of functions, so the theorem actually like expands the boundary of this function of the functions. So it's like trying to find the more the to try like find trying to make the condition less stricter and satisfy more general conditions. So let's see how to prove it. So the first part, we firstly prove the result A. Okay. To prove that Fn is uniformly bounded on K, the idea is basically we try to show that for all functions that have a bound, we can actually find a certain bound that works for all these functions. Okay. So firstly, we do something tricky. It's not that tricky, but we do play something on the compact set K. Okay. So let's first cover K with a set of neighborhoods. And since K is compact, so we get that actually there exists a finite subcover and delta xi is from 1 to infinity. Okay, this is the property of compactness of K. So now, since Fn is pointwise bounded, we're going to use the second condition, pointwise bounded. Since Fn is pointwise bounded, then at each xi, so we can cover the set K with a finite subcover. So at each point xi, there exists mi, such that Fn xi is bounded by mi, right? Because it's pointwise bounded. If we like fix a point xi, now we can find a bound satisfying for this point xi. And well, for the point that we choose, well, we now the subcover is fine. Now the number of subcovers are finite, right? So if we take only those finite points, if we take x1 to xn, then it must satisfy that Fn xi is bounded by mi, right? But what if we take some points that is not the points, not the central points of the neighborhoods. Something like, okay, let's say if we only take it on here, x1, x2, x3, x4. Well, here we got some like, we have some like neighborhood. If we take these points, it satisfies the result that fn xi is bounded by mi. But what if we take something like here? It's not in the center of the cover. What are we gonna get? Actually, since it's not the center, it's not in the central point of the neighborhood, but it's still in the neighborhood of the. It's still in the neighborhood of that central point, right? So it's not gonna get too far away because K is compact. Remember, K is compact. So actually, we can find some M. We can find M to be let M to be the maximum of mi plus usual. And now we prove that for any x contained in K, now we actually take x from K. We have fn x, the absolute value of fn x can be written as fn x minus fn xi plus fn xi. So it is smaller than fn x minus fn xi, absolute value of its two terms, and absolute value of fx and I. And the choice of xi actually dependent on where you choose x. So xi is the central point of x, of the neighborhood of x. Actually, x is the central point of the neighborhood that contains x. So you may get that this is quite simple because they're in the same neighborhood, right? So fn x minus fn xi must be smaller than epsilon, and for the central point xi, fn xi must smaller than mi. And now we show that it is smaller than m. So we find the m that satisfy all the condition, or we find such m that is a bound for all the functions. Okay. So we prove that we can find such kind of bound that works for all functions. So now we get the result. Fn actually is uniformly bounded on K, right? Okay, now let's move on to the second result. Actually, before we get access to the proof, I'll first give you a lemma. And if you're familiar with like the compactness, it's already a result. It cannot be like called a lemma. It's just a very simple result about the compactness of a metric space. So if K is a compact metric space, then there exists a countable dense subset E, which is contained in K. And this lemma can also be interpreted as every point of K, PT is abbreviated for point. Every point of K is either in E or is a accumulation point of V. Accumulation point is also limit point. And this result is quite critical. We're going to use it in the following proof. So, well, by the previous theorem, we've already showed that under such kind of condition, there actually exists a subsequence f and k that is pointwise convergent on E, right? But the thing is, now we are the condition is much more is somehow like more sophisticated, and we want to show that the subsequence f and k is not only pointwise convergent on E, actually it's uniformly convergent on E. Because so we now claim. So claim is like what we are gonna show. We claim f and k is actually uniformly convergent. So now let's prove it. The idea is still the same. Basically the definition plus the classic method, triangular inequality. Okay, and we will also use the Cauchy criteria for uniform convergence. So still we fix epsilon because, well, we try to prove that given epsilon larger than 0, there exists some n or some epsilon we are trying to. Given any epsilon larger than 0, by Cauchy criteria, we want to show that there exists a capital N. Okay, I think I'll still write it down. Want to show that given epsilon larger than 0, there exists a capital N such that for kr larger than n and x is an element in k, we can imply that f and kx minus f and rx, the absolute value of f and kx minus f and rx is smaller than epsilon by Cauchy criteria. So, still the same, we fix epsilon larger than 0, and now the condition says that it is equicontinuous. It is a set of equicontinuous functions, right? We've already proved in the previous theorem, right? Fn is equicontinuous on K. Sorry, I should say by equicontinuity. In previous theorem. If you don't remember, please go back and check it. There exists some delta larger than 0, such that for any 2 points with distance less than delta, we can find the distance between f and kx and minus f and rx is smaller than 3 over epsilon, right? Okay, now still, since we are given a compact metric space, compact set, so we cover every point in E with the set of neighborhoods and delta E, where E is element in E, in capital E. So now, since E is dense, remember we haven't used the property of dense. Since E is dense. Okay. Now we know that and it is also the result in like the compactness and density of metric space. So I'm not gonna prove it, but if you're interested in it, you can check it either in the book or you can search it online. Okay. So since it's dense, we know that this set of covers also covers K. Sorry. Right? It's actually very understandable because, well, every point in K, as I said here, every point in K is either in E or is a accumulation point of E. So the point in K is actually in the closure of E, right? If X is in K, then X must be the closure. X must be in the closure of E. Okay. Still by compactness. There exists a finite set of neighborhoods, EI. Now I is from 1 to P. Finite cover of K. Finite cover of K. And now, since we know that F and K converge pointwisely on E1, E2, blah, 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 to EP on the set of points, and this set is actually finite. So by pointwise convergence, we can get there exists N such that for KL larger than N, and the N we take here is the maximum of N1 to NP. I think I'm sorry if this might like confuse you, because N1 to NP here, the N does not mean the neighborhood. It means the N that you choose to satisfy the condition for pointwise convergence. So here the capital N is equal to the maximum of all the N you choose to satisfy the pointwise convergence. So for KL larger than such kind of N, we actually have F and K EI minus F and L EI. Is smaller than 3 over epsilon. And here I is from 1 to P, right? Okay, now finally get to the triangular continuity. Now, here, so now here, we are trying to look for a arbitrarily chosen x. So then for any x which is contained in K, if we are given KL larger than N, then we will have F and Kx minus F and Lx. So here x is arbitrarily chosen, and we want to like make some connection to the arbitrarily chosen x and those points that is in the finite set U1 to EP, right? Because in that case we can use the inequality we just showed, right? So still by the triangular inequality, and we can separate the absolute value of these two terms into f and k x minus f and k ei plus f and k ei minus f and r ei plus f and r ei minus f and r x. And still, here the choice of ei depends on x. So whenever you choose, you first choose x, then you find the central point of the neighborhood where x lies. Okay. So now we get the first term is smaller than epsilon, right? Because the equicontinuity, right? So because of the continuity of functions, and the second term is also smaller than epsilon over 3, and the second term is also smaller than epsilon over 3 by what we've just shown, and the third term is also. So the whole term here is smaller than epsilon, right? Just to be careful here, the choice of ei depends on x, but you have to know that whatever x you choose, you will always find such kind of ei because of the compactness of k. Okay, now finally we reach the result of Ascoli-Arzela. We find such kind of uniform convergent subsequence. In fact, it's like we prove that f and k is uniformly convergent. And f and k is a subsequence of the original sequence, right? So in the previous theorems, we find the subsequence f and k, and we prove that it's actually pointwise convergent. And now we further explain that it's not only pointwise convergent, it's also uniformly convergent. So we get to the result of the theorem. So that's it. That's what I want to talk about Ascoli-Arzela. And if you have any questions, or if I made any mistakes, please leave me a comment or send me emails. And hope you enjoy it. And bye bye. Thank you, guys.